the final black box. Why physics forbids us from understanding AGI. Imagine creating an intelligence whose reasoning disappears the moment we try to observe it. According to quantum physics, that future may be inevitable. A foundational principle of quantum mechanics dictates that the very act of observing a system irreversibly collapses its state, destroying the information it contains. This physical law presents the ultimate barrier to AI safety and oversight, suggesting that any attempt to reverse engineer the reasoning of a future quantum AGI would inherently erase the very computation we seek to understand. By first analyzing the limits of classical interpretability before delving into the amplified opacity of quantum systems. A synthesis of research from the frontiers of physics and computing reveals that we are on a trajectory to build an intelligence whose inner workings nature itself forbids us from knowing. Before the prospect of a quantum black box emerged, the field of artificial intelligence was already contending with a profound and persistent crisis of comprehension in its classical systems. The term black box is not a casual metaphor, but a precise descriptor for the operational reality of today's most advanced deep neural networks. A paradox where superhuman capabilities is directly coupled with subhuman explainability. Even with complete, granular access to a model's underlying architecture, every simulated neuron, every weighted connection, and every mathematical activation function, the path from input to output remains fundamentally inscrutable to human analysis. This opacity is not a result of hidden code or proprietary secrets. It is an emergent property of the very method by which these systems learn. A model designed for a complex task like image recognition or natural language translation comprises millions or even billions of parameters that are iteratively adjusted through automated optimization processes on vast datasets. The resulting knowledge is not stored in discrete logical rules, but is distributed as a diffuse pattern across this immense high-dimensional vector space. The nonlinear transformations applied at each layer of the network ensure that the relationship between any single parameter and the final output is context-dependent and entangled with the state of every other parameter, making a linear, causal reverse engineering practically impossible. Research from leading institutions, including extensive investigations detailed in DeepMind research, and a continuous stream of studies on platforms like Arxiv, has focused on developing interpretability tools. Yet these efforts have yielded limited success. Techniques such as saliency maps can highlight which input features a model deemed important, but they fail to explain the deeper associative logic or the abstract concepts the network has formed internally. We can see what the model is looking at, but we cannot truly understand why it has learned to associate those features with a specific outcome. A critical failure when deploying these systems in high-stakes domains like medicine or autonomous navigation. This existing interpretability gap in classical AGI frameworks already represents a significant technical and ethical barrier, establishing a critical precedent for the amplified complexities to come. The central problem is that even with total access to its structure, the reasoning of a classical deep learning model is an emergent property of its vast, distributed, and nonlinear architecture, rendering its internal logic fundamentally opaque to human auditors. The transition from classical computation to the quantum domain elevates the black box problem from an issue of immense complexity to one of fundamental ontology, where the classical system's opacity is a product of scale. The opacity of quantum machine learning QML is woven into the very fabric of its physical substrate, presenting what could be termed an interpretability crisis in quantum machine learning. The operational principles of quantum neural networks are not mere accelerations of existing methods. They represent a qualitative paradigm shift in how information is encoded and processed. This shift originates with the quantum bit, or qubit, Unlike a classical bit, confined to a definite state of 0 or 1, a qubit leverages the principle of superposition to exist as a probabilistic combination of both states simultaneously, as outlined in foundational papers published in journals like Science, and further explored in theoretical work from institutions such as the Perimeter Institute for Theoretical Physics. A system of n qubits can therefore represent 2^n states at once. This capacity grants quantum neural networks access to an exponentially vast computational arena known as Hilbert space, a multidimensional state space where solutions to certain problems can be explored in parallel. Furthermore, these systems harness entanglement, a non-local correlation where the state of one qubit is inextricably linked to the state of another, regardless of separation. This phenomenon allows for the creation of intricate, non-classical relationships between computational units, forming a processing logic based on holistic correlations, rather than discrete, sequential operations. Consequently, the knowledge within a trained QNN is not stored in the adjustable weights of its connections in a way analogous to classical AGI. Instead, it is encoded within the delicate probabilistic amplitudes and phases of entangled quantum state, as documented in numerous preprints on Arxiv. Attempting to apply classical interpretability techniques to such a system is a category error. One cannot generate a saliency map for a decision derived from a superposition, nor can one trace a causal chain through a web of entangled quantum logic gates, because the underlying logic is inherently probabilistic and globally correlated, not sequential and localized. The computational substrate itself operates on principles that lack direct analogs in our macroscopic classical experience. The core challenge of quantum machine learning is that its immense computational advantage is derived directly from leveraging quantum phenomena like superposition and entanglement. Phenomena that process information in a probabilistic Hilbert space, qualitatively different from and irreconcilable with the discrete, deterministic logic of classical systems. Ultimately, the impassable nature of the quantum black box is not a limitation of our engineering or analytical tools. It is a direct and unavoidable consequence of fundamental physical law. The core of this barrier lies in the measurement problem of quantum mechanics, a principle that has been a cornerstone of quantum theory since its inception, and is central to the operational logic of any device harnessing quantum effects. Within a functioning quantum computer, information processing occurs while its qubits exist in a delicate probabilistic state of superposition and entanglement. This quantum state, described by a wave function, contains the full richness of the parallel computation. However, the act of observing this system to determine the specific values of its quantum logic gates, the very process required for any meaningful audit or interpretation, is an inherently invasive event. This is not a passive reading of data. It is a physical interaction, BOT1, that forces the entire system's wave function to collapse from its complex probabilistic form into a single, definite classical state. The moment we attempt to look inside the quantum black box to understand its reasoning, the quantum computation ceases. And the unique informational state that constituted that reasoning is irrevocably destroyed, leaving behind only one of many potential classical outcomes. This physical constraint makes the internal logic of a quantum AGI literally unobservable in its native operational state. This principle is not merely theoretical. It is manifested in the extreme engineering required to build and operate quantum hardware. As demonstrated by the architecture of systems like the IBM Quantum System 2, processors must be isolated within cryogenic environments at temperatures colder than deep space, shielded from the slightest external perturbation to prevent premature decoherence. The unintentional collapse of the quantum state. The intense efforts to maintain this isolation explored in areas like MIT Cryo-CMOS interface research underscore the profound fragility of quantum information. The very structure built to protect the computation also renders it inaccessible. Therefore, we are faced with a profound paradox. The properties that grant quantum machine learning its immense power are the same properties destroyed by the act of observation, placing the inner workings of a future quantum AGI beyond any possibility of direct reverse engineering. The fundamental laws of quantum mechanics dictate that observing the internal state of a quantum computation is an inherently destructive act, one that collapses its probabilistic reasoning into a single classical outcome. The progression from classical to quantum systems demonstrates that the AI black box is not an engineering challenge to be solved, but a fundamental boundary imposed by physical law. This reality transforms the challenge of AI safety from a problem of reverse engineering to one of managing a system whose reasoning we are forbidden to observe by nature itself. The very measurement required for oversight is the act that erases the knowledge we seek, forcing us to confront the possibility of an intelligence we can create, but never truly comprehend. If this in-depth analysis provided value, please support Tech Dissect Official by liking this video and subscribing for more content that goes beyond the headlines. Given that the internal logic of a quantum AGI may be physically inaccessible, what new principles of trust, verification, or ethical containment should humanity develop before such systems are deployed? Thank you for thinking deeply with us. Next time, we move from the quantum to the biological, as we investigate the emerging frontier of organoid intelligence and the profound questions it raises about the nature of thought itself.